Okay, good afternoon and welcome to this talk. This is the second part of a presentation titled Regret Lower Bounds in Qualcomm Bandits and Reinforcement Learning. So we had up to this slide coming to reinforcement learning in MDPs, and we would like to investigate what is the regret lower bounds.
Can you just tell a very brief introduction, because I wasn't there in the previous.
So we started with a very brief introduction of the general setup of online decision making. So this is the very general setting of the whole big class of online decision making problem. Basically, we consider a time slotted system where at each time step t1 to up to time horizon capital T, a decision maker observes a state S of t at time t, and then she chooses an action A of t from a given action space denoted by calligraphic A, and to do so she employs basically she determines A of t as a function pi of all observed history so far. Basically, the decision maker observes the sequence of her current state, her chosen action at that state, and the received reward. Then the next time, the next time, the next time. And when she is at time t, she observes S of t, and she chooses A of t as a function of all this history so far. This is very, very general setup, and this pi could be a very complicated function.
And the reward according to each action is, the distribution is known, or what do we know about this?
The only thing that the decision maker basically in this kind of setup knows is she knows what is the state space, and she observes the current state. So it's not partially observable system. It's not that much, but she knows what is action space. Basically, what is the available action at a given state, and what is the state space. She doesn't know anything more. So this is very, very limited information that she receives, that she has. But she only makes this observation: what is the state, for example, S1, and then which state she has transited to, and what is the reward in various states, various actions in various states. So when we specify to multi-round bandit or to Markov decision process, which are subsets of this model, I think it becomes more clear. What is important here is that the goal of decision maker basically is to maximize the notion of reward, and in this specific. So for the moment, to simplify things, let us assume that the goal is to maximize the collected reward, but it could be a collected reward within episode or collected discounted reward as well. And this is very important. Observations and rewards are generated by an unknown environment. Basically, the only thing you know in advance as a decision maker is the action space and state space. If you remember, we told that we have several performance metrics, but one performance metric of interest is the notion of regret, which compares the difference between the expected cumulative reward under an optimal policy, pi star, and the policy that you employ. So basically, this optimal policy can be computed maybe in a very complex way when you know what is the environment. And in this respect, this notion of regret basically compares what you could get in the best case if you would know all the unknowns of the environment in expectation minus what you would get under your algorithm, right? So basically this is the expected value of cumulative performance loss. So at each time t, you lose this loss, you lose this amount of reward, RT under pi star minus RT under pi, and cumulatively sum of this and if you take expectation, it examines what is this cumulative loss in expectation.
So the expectation is over the states that we observe.
All possible randomness. This is randomness in the reward because rewards could be random, but could be deterministic as well. There is randomization in the algorithm as well because you may randomize. Okay, because this function pi I showed here could employ some randomization as well. So there is a random seed that could be in
right.
And also the expected value is with respect to initial state and also with respect to basically state transitions, with respect to everything. So basically if we provide any regret bound, any bound on this notion of regret, it is very strong bound because it controls all these randomness. Right? We also said that the goal of decision maker is to maximize this cumulative reward, right? And this cumulative reward is a random variable, so you either maximize this notion of reward in expectation or in high probability. But at least you can see that in the expectation it is equivalent to minimize the regret, right? If you minimize the regret, since this is not under your control, you maximize the expected value of cumulative reward, right? And to do so, you as a decision maker have to hold some trade-off or to balance the exploration versus exploitation. Basically, at each time step, you have made some observations so far, but you have not explored maybe the environment perfectly, and this is the case when t is a finite time, right? Basically, you have the choice, or your algorithm has the choice of either playing the best action empirically so far, which is to act consistently based on the gathered history, or to explore another action which is not tried maybe oftentimes. So this is the famous exploration-exploitation trade-off. And because of this exploration-exploitation trade-off, this notion of regret and this general setup captures a wide range of problems. And this wide range of problems basically range from problems in engineering domains up to operation research domains. So this is still very general, and one specific setup that we studied was the case of Qualcomm Bandits. Qualcomm Bandit basically can be captured easily by this specification here. I review it here because today I'm going to discuss the case of Markov decision process, which itself is a superset of Qualcomm Bandits. So this is Qualcomm Bandit. Basically, we have a set of k arms. Each arm A is associated with a probability distribution nu of A. This nu of A is a probability distribution not necessarily of bounded support, but basically it could have any distribution. For the moment, assume that the mean of nu A is nu of A. There is no notion of a state, or let's say there is a notion of a state, but the state space is a singleton. So it's symbol in that space. If you select an arm A, it leads to a realization from a sample from this distribution nu of A. So basically, this sample will be called cost or reward of RA, and then in the literature it's usually referred as to reward because you would like to maximize it. But you can alternatively think of minimizing the cost, and you may call it a random cost according to this distribution. Anyway, you have, according to choosing an arm A, you draw a sample from nu A. What you know in this setup is that what is the set of arms. You don't know anything more. Right? You are given a set of arms, k arms, that's it. You don't know anything about nu A. Right? What is the goal? The goal is to maximize the sum of rewards collected after let's say t time steps, either in expectation or with high probability, but let's for the moment restrict ourselves to expectation. So basically, if you know what is mu A for all arm A, what is the optimal solution? The optimal solution is always play the arm with the maximal mu A, which we call it mu star. But you don't know, so you have to gather sample and you have to try different arms so that you may you maintain empirical means of various arms at different times. Yeah, well, this is continuation of the model. At time t, you choose arm t, and upon choosing arm A of t, you choose arm A of t. Upon choosing this, you observe this reward, right? This is capital A of t, and this A of t, capital A of t, is chosen based on all the information gathered so far. This is just similar to what we said here, right? But here you have notion of a state. In Qualcomm Bandits, you don't have notion of a state. This was the Qualcomm Bandit model we discussed last time. This is the goal, to maximize this, or equivalently to minimize this regret. But the regret here can be simplified as this, because there is no notion of a state, and the optimal reward, or the reward under an optimal policy, is simply after t time step is t mu of A star on average. And this is something constant. You can bring it outside of expected value. So t mu of A star is what you would get on average under an optimal algorithm, or equivalently under the case that the environment is known. And this value is what you would get when you don't know anything. So in that sense, the notion of regret is very fine performance measure. We have another performance measure that is, so to say, coarser than this. And this is to make sure that to make sure, for example, you maximize R of t, but not under expectation. Or you maximize sum of R of t divided by t. So this expected value here plays central role, because there are fewer policies, or much more restricted class of policies that minimize their regret, whereas there are bigger class of policies for which in the long run you maximize this sum. Okay, so we discussed regret lower bound for this model, and let me jump over this because it takes some time to go over all this. So we had this essential result for regret lower bound, but I may not review this here, but when I state this, the results similar to this for Markov decision processes, I try to maybe come back to this and then use some of the analogies. Okay, so we are here. We are considering what is known as undiscounted reinforcement learning. So basically, this reinforcement learning is a specific class of that general decision-making setup we described at the very beginning of this presentation. So here, basically, we have several classes, but here only we consider undiscounted reinforcement learning. We have a decision maker that interacts with an unknown environment, and we make it precise what do we mean by unknown. So we have an unknown environment, and environment is that can be modeled as a finite Markov decision process without any discount. So Markov decision process, abbreviated as MDP, is a tuple shown by M. So is a tuple a state space calligraphic S, action space calligraphic A, set of reward functions nu, and transition kernel P. Reward function and transition kernel, these two are unknown to the decision maker. So basically similar to Qualcomm Bandits or the very general setup, the decision maker knows what is a state space or action space, but doesn't know what is a reward function or transition kernel. What is the role of a reward function and transition kernel? So to complete the model, we have this. If you are at state S and if you choose action A, you receive a random reward that is a function of SA. It could be random or it could be deterministic, but it is a function of SA. In the most general setting, we assume that this reward is drawn or sampled from the distribution mu of SA, and we assume that the mean of this distribution is denoted by mu of SA. So if it was multi-bandit, you just forget about S, and everything is as if you have arm A. So this action space is similar to arm space at a given state. For simplicity, we assume that this action space is the same over all states, but you can simply assume that this action space is action space of S, like this. You can assume that you have different set of actions at various states. But for simplicity, we assume that you have the same action space at any state. We have transition kernel P. This is collection of transition probability distributions in the following sense. If you select action A in a state S, this leads to a transition to a state S prime with probability P of S prime conditioned on a state S action A. So basically this P of S prime condition to this is a probability vector. So sum of all these probabilities sum to 1, right? Because either you state in your current state or to state to somewhere, it should sum to 1.
Right. And here, sorry, the state space S, this is a discrete space.
This is discrete. Yeah. This is finite MDP, and finite MDP means that you have finite.
Yeah, exactly.
Yes.
Finite.
Otherwise, the next step to generalize this is to assume that you have still finite action space, but you have continuous state space.
Right.
But
yeah.
Even for this, still the life will become very complicated. But you can, in the next stage, well, let me have this terminology here because it's going to be useful. When you have this as a finite MDP, this reward function and transition function would be called reward function and transition function.
Yeah.
But when you have this state space continuous or this action space continuous, this is for sure is called kernel. That's why it's.
One thing, no and P, they should be stationary, right?
Yeah, this is stationary. Yeah, these are
okay,
time
you
invariant.
said that, but that's okay.
So in the general case, this is P of T, but what we assume is that the environment is finite and stationary. Yes, there is no. Normally, it's stationary because if it's well, this is Markovian and stationary state transition. Yeah, there is no dependence on T. So even with this finite and stationary model, there are a lot of applications that would fall in this model, in this framework. And if you extend this set of problems to non-stationary and continuous state space, this application class becomes very, very rich, and it's very. It would be very hard to find some application that that falls outside this. But these specific applications that may fall outside this would constitute, for example, those where a state transition is not only as a function of your current state, but also as a function of your history.
Right.
So this would be related to time series, and things there is very, very complicated. So it's keep in mind, reward function is not known. Or maybe reward function is known, but at least its mean is not known. Transition kernel is unknown, and this is the main hardness. The decision maker has some goal. We continue in the next slide, and as you can see, you will see. But the thing that limits her is that these two are unknown. You can assume that reward function is known, or even reward function is deterministic, so that if you visit every state and if you try every action, each action in every state, then you basically would know what is reward function. But still, if you assume that P is unknown, the problem difficulty would be almost the same.
Yeah.
So the bottleneck would be unknown transition kernel, because this is outside control of decision maker. This is what is dictated by the environment. So this is the objective of decision maker, which is generalization of what we have in the multi-arm bandit. The decision maker would like to learn a policy that has the maximal gain. What is the gain? If you have a policy pi, and if you start from a state S1, this would be the average reward of decision maker when she starts from a state S1 and follows policy pi all the time. So basically, a policy which is not made precise here is in general, a policy is a mapping from states and history to a set of probability distributions over action space. Yes. But
infimum is over what?
one moment, yes.
Expectation is over reward?
Yes, let me present all the ingredients here, because that would be, I think, for the moment, forget about infimum. For the moment. So basically, if you look at this, we only consider Markov deterministic policies. Basically, a policy could be a very, very complicated function. A very complicated function that takes as an input your current state and your history so far. And this policy is different than the policy I had here. This is different than the policy. So it's bad notation that probably we use here. So try to forget about this slide. This is a policy in the case of MDP. So when we talk about multi-arm bandits, we use this pi as the pi in general setup. But when we talk about MDP, this is the pi for the MDP. And we talk about algorithm A. So we will talk about algorithm A. That is what you would implement. This policy, pi, is what you would have even if you know the MDP. This is what you, for example, compute by value iteration, policy iteration. For the moment, assume that there is no learning. You know everything, so there is nothing to learn. It's just something to compute. This is a discounted setup, and you would like to maximize the sum of the reward. And there is a theorem saying that the policy that would maximize the sum of reward, there is an optimal policy that is Markov deterministic. A Markov deterministic policy is simply a policy that that is only a function of a state. That is only a function of a state. So accept this fact. It's an important fact that if you have an MDP, this holds for discounted, undiscounted, for everything, for all MDPs. If you have an MDP, and if you search for a policy that maximizes sum of rewards, there is a policy that does not require any randomization. That is Markov deterministic. A Markov deterministic policy, refers to the fact that it does not employ any randomization, and Markov refers to the fact that it does not require anything about history. A Markov deterministic policy is simply as this. It takes as an input what is your current state and gives you what is the action. So it's simply a mapping or a function from state space to action space. It says what your current state, you say I'm in this state. It says, okay, go for this. So this would be a policy, and the optimal policy is some policy that's among this class of all policies. So basically, here R of S of t and pi of S of t says that fix a policy pi, and a policy pi is just a mapping from a state space to action space. Just at each state, start from S1, and at each state, see what action would be output by pi of S of t, and then the reward would be R of S of t and pi of S of t, right? Mm-hmm. So there is no randomization in the policy. And then if you sum this over t from 1 to t, capital T, mm-hmm. It would be what is the reward that you would collect if you start from S1 and just applying policy phi. Yeah. Okay? And then if you divide it by t, so forget about the expectation, it would be your average reward, right? So now if you take expectation, this expectation takes into account that S1 could be random. Sorry. For the moment, S1 is fixed. Yeah. This takes into account that your reward could be random. Also, the action is fixed, but it is drawn from a distribution nu of SA, right? It could be random. Right. And also, if you are at a state S of t, and if you choose this pi of S of t, the environment brings you to another state decided by this policy that you have chosen, and this state that you have not chosen, you are brought to, but because of the kernel that is out of your control. Right. So everything is known here, yet no learning. And if you take, if you look at this quantity when t goes to infinity, this is just the average reward, right? Of course, this may not exist, the limit, and you have infimum here. It's because of measure theoretical stuff. There is no maximization here. So this is the average reward under policy pi in the even without learning when you start from S1, right? If you have discounted, you need not this infimum, and you would not divide by t, and you would rather have gamma to the power of t, discounted type. This is called the gain of policy pi when you start from S1. And of course, in the general setup, it's a function of initial state. It is referred to gain or average reward. And the optimal policy is the policy that achieves the maximal gain, which is a function of S1, and this is by taking the maximization over all possible policies, or equivalently, or all possible. I have soup here. Yeah. Why? Because there are finitely many stationary policies. This is just the number of functions from a state space S to action space A. How many of them we have?
Finite because the MDP is
it's
finite.
a to the is all the functions a to the power of s. It's exponentially many in s, but it's
right. Yeah.
It's we know from combinatorics all the functions from set A1 to a set A2 is related to the cardinality of the two sets, right?
Right. Yeah, exactly.
So then the soup, there is the soup, but we replace it by max. So now we go towards the learning. And for the learning side, we have an algorithm A that to choose action A of t, the algorithm may take any complex function that takes as an input your current state, the history so far. Remember that you observe what is a state at all times less than t, and all actions chosen there, and all the rewards received there, right? And this is the history, and this is your current state. And we have an algorithm. Basically, this could employ any function that also could employ randomization, and then outputs one action A of t and says, okay, this is your current action. So, well, the main objective of decision maker is to identify a policy that has this gain, G star. But to see what is the how good is the decision maker is acting towards learning this policy, we have regret. The regret of this algorithm A up to time slot capital T, when she starts from a state S1, is what you would achieve in the average under the known case, which is the case when you know your MDP, basically. When you know your MDP, you can compute optimal policy, and on average, you would receive a TG star, right?
Right. Yeah.
It makes sense, right? On average.
Yeah.
But what you would receive is this. It's very simple, right?
Yeah, exactly. Yeah.
So this is regret, and I can argue it's very fine performance measure, in the sense that it's very hard to come up with much better performance measure than this. It's very strong because any upper bound on this, basically, would compare what you would achieve under the case, against the case that you do not know your MDP, but also compares to the trajectory taken by the optimal algorithm.
Right, and the optimal here would...
There is an expectation. So basically, we can have expected value of this under the optimal algorithm minus this. This, basically, we can have similar term here, but for the optimal algorithm. For the action under optimal algorithm and for the trajectory followed by the optimal algorithm. But if you take the expectation, this comes out plus a term that is related to mixing of the Markov chains. That term is finite, basically. And in that sense, this regret is related to this notion of regret you are stating.
But finite given some conditions on the MDP, I guess.
Yeah, well, that condition I'm just bringing.
Oh.
Yeah, but that's right. This is the more precise notion of regret, but we can make it precise why we go for this. Because controlling this notion of regret is equivalent to controlling that. Of course, they differ up to some terms that are of higher order term. So this S1 is very irritating now, because it says your optimal gain, your whatever is dependent on the initial state.
Yeah.
Is it necessary? Well, we have in many application domains the class of communicating MDPs, which is big enough. For example, a lot of applications that can be modeled by Markov decision processes are communicating MDPs. Those MDPs under which from any state to any other state you can traverse in a finite time in expectation. It makes sense. I mean, if you are not trapped somewhere, it makes sense.
Is it like ergodicity or?
This is weaker than ergodicity. So basically, you go to point. So we have ergodic class. In ergodic class, under any policy, you reach from any state to any other state in finite time in expectation. But communicating MDP says that you may not reach under any state to any other state under any policy, but under some policy. So basically, in any ergodic MDP is communicating but any communicating MVP
Yeah.
is not ergodic. For example, if you
That's a bigger,
if you for example model this maze thing or this kind of tasks as an MVP, usually they are not ergodic. If you make ergodic assumption, the life is much simpler. It's still not very simple, but much simpler than communicating. But all these problems are communicating because, well, there is somewhere that you can go from a square 1 to a square, for example, 10, and vice versa. We have a still class of MDPs that you can go from a square 1 to a square 10, but not the other way. So these are not communicating. But if you assume that from any state to any other state, you can travel under some appropriate policy, not under any policy. Because if it's under any policy, it's ergodic. Otherwise, it's only communicating. So for this communicating class, G star, and of course equivalently the regret, does not depend on the initial state, which is good. Your performance measure and your optimal policy is independent of the initial state. So basically, as time goes on, the MDP forgets about this initial thing. So this is good. We get rid of this S1 from so on. So we need a little bit of preliminaries. So basically, we talked about G star. We talked about optimal policy, but you should know how you would compute if you know the MDP. So basically, optimal policy satisfies this set of fixed point equation for any state S, G star plus some function B star, that is a function of a state, is equivalent to max of this plus this. Well, this B star is viewed here both as a function and as a vector. So basically, let's treat it as a vector. So this is this can be argued like in the spirit of backward induction. Basically, it says that if you are at the state S and you choose action A, and the rest of the time, basically, so basically it says under the optimal policy, if you choose max of this, it would be your G star, your long-term average reward, plus some offset. And this offset is called, denoted by B star, it's called the bias function. If it was discounted, there would be discount factor here, gamma here, and this B star would be 0. But if it's not discounted MVP,
Explain
you
the
have
second
this.
term in parentheses. What is that exactly? The B star is the same as B star of S?
Yes.
So it's
This
still-
B star, yeah, well, let me write it here because it's it would be more intuitive.
I guess the first term is the immediate reward and the second term is...
Immediate average reward, indeed, yes. So this is what you would get when you are at state S and choose action A. And action A could be suboptimal. It would be mu of SA plus you may transit to another state under action A, which would be with this probability, and you would have this offset, B star of Y, right? And by Bellman optimality principle, it would be equal to G star plus DSP star, but evaluated state S. And you would have this simultaneously for all states. So to further discussing about this is a bit beyond for the moment, but what is important here is that you have a quantity called bias function that plays a central role in regret bounds that we will see in the sequel. So G star here is the maximal gain, and this bias function can be computed up to an additive constant. Because if I give you a bias function V star, if you plug in V star plus C, where C is a constant, the equation holds. So this can be determined, this bias function, up to a constant. So what is interpretation of this bias function? This is basically the relative gain that you may start at a state S rather than a state S prime. It says you would get average gain of G star if you start in any state, but up to this V star of S. So it's some slack. So these are a set of fixed point equations. You can cast it as an LP and you can solve it. So if you know what is P and what is nu, because if you know nu, you know what is mu as well, you can solve this fixed point equation. You can find G star. You can find the policy maximizing achieving G star, and you can find the bias function. So that would be it. And there are polynomial time algorithm to do so, because it would be cast as an LP, and as long as your MDP is finite, this is polynomial time, right? But what we talk about learning, and we talk about an MDP that is governed by this Bellman optimality equation. So we introduce this to introduce further relevant quantities. One relevant quantity is the gap phi of SA. Which is basically defined in view of this Bellman equation. Basically, if you look at the right-hand side, this maximum is obtained when you take the optimal policy for some action A. But for any other action that is not achieving this maximum, there would be some gap, right? And this gap, if I denote the optimal policy by phi star, would be this. The mu of this SA, the distance of mu of SA, where A is suboptimal to this, under optimal, minus this. We come back to this a bit later. But when you have bandits, the bias function is 0, and these transition probabilities do not exist, basically. You don't have this. So any gap, notion of gap that you have in the bandits only has this, right? Just the average gain of the optimal reward minus the average gain of the average reward of the optimal arm minus the average reward of suboptimal arm A. The other thing that I introduce now that could be interesting because we discussed about so far is notion of diameter. It's introduced in the paper by Jack et al. In 2010. So remember this class of communicating MDP, where you can reach from any state to any other state in finite time in expectation. Right? So we make it precise here. So basically, let T pi of S prime given S, you know, the first hitting time when you start in a state S and you reach a state S prime in expectation, right? Under the stationary policy pi. So this means that you start from S and always you apply action pi of S in any state along your way. The diameter D of an MDPM is this. So basically the burst traveling time between any pair of states, right? Under the best policy that does this in expectation. This makes sense, right? If you forget about this maximum, this inner quantity is the fastest time you can travel from S to S prime under the best policy that you can travel, under the fastest policy, right? And if you take the maximum over all pair of states, right, this would be the worst traveling time, and we call this diameter, and it makes sense, right? So we have this surprising fact, not surprising, that any communicating MDP has a finite diameter. Right? It's good. So we talked about a span function. You can view it as a vector, as a function. We simultaneously do this. When we view this span function, span as bias function as a function, we look at its range because it's some quantity of interest that will be appearing later on. So it's just range of this span function. The maximum value over all the states minus its minimum value. And we have again this fact that the span is less than diameter. What do you expect about diameter? How big it would be? Or how small?
B is a scalar or a vector? If vector,
it's a vector. If it's vector, okay, B, forget about its function property. It's just a vector.
Okay.
It's a vector, and its dimensionality is number of states.
Okay.
Right? This is just a maximum value of this vector minus its minimum value. And of course, you can set the minimum value to 0, and then it would be the infinity norm. But in general, we use the term span as introduced in the literature. So this is the range of your value function. So let me introduce this terminology here. This bias function in some literature is referred to as relative value function, because it's the relative value when you start in this state rather than the other state. In some other literature, it's called potential.
But couldn't it be something like the long-term reward? Because that iteration that you just wrote there is like immediate reward, which is mu plus some in which state you are going multiplied by the reward if you go from that state and then following the policy onward. And if so, it
since you can put G star here and G star here, it would not matter. It would have the same interpretation as you say.
Okay. Because
since it is determined up to an additive constant, it's this interpretation that you say holds here. So it would be it admits this Bellman equation admits the same interpretation as in the discounted case. In the discounted case, it's more intuitive probably, but it has the same interpretation here. It's a bit more complicated probably, but it admits the same interpretation. So we introduced this bias and span of bias and diameter because these are relevant parameters in MDP. Basically, when we discussed about learning, we would like to see what is the hardness of learning. So when we talk about multi-arm bandit, we know already what is the hardness of learning in the bandit model. The MDP model that we discussed here is a generalization of bandit model, but here we have additional state transition, and because of this state transition, we should have some notion of complexity beyond what we have in bandits, right? And we need these kind of notions. Okay, I can further continue. Everything is, as for preliminaries, it's presented so far. And we are now ready to look at one actual algorithm. It's not the state-of-the-art algorithm, but one actual algorithm that can be used for learning in MDPs. Right? Everything is ready. Why not trying this? So I introduced this notation. NT of SA denotes the number of visits to S state S, an action A, a state action pair SA, right? Up to time t. So it means that from time 1 to time t minus 1, excluding time t, how many times I have been in a state S and chosen action A. Very simple. Similarly, NT SA S prime is number of visits up to time t to SA, where a visit to a state S prime is followed. Right? Oh, sorry. We don't know what is the average rewards and what are transition probabilities, but we can at least empirically estimate them, right? So this is simply notations for empirical estimates of average rewards and transition probabilities. Given this notation, the empirical transition probability of S state S prime when you are SA up to time t, of course this is time varied, right, is computed as this, where this plus here is to make sure that you do not divide by 0. So this is just a solution to maximum likelihood estimate of estimation. And this is mu hat of T of SA, the empirical average reward, right? This is just the sum of the rewards that you have received when you have been in a state SA divided by number of visits. Very, very simple. So with this, we can now present one algorithm, but it's not only one algorithm, it gives the key to a meta-algorithm that if you change that algorithm a little bit, you easily recover some other algorithms. So the algorithm we present here is UCRL2. It stands for upper confidence bound for reinforcement learning number 2, where there was not number 1, there was UCRL first, but this is the modified version that actually works. So it is presented in the NIPS paper 2009 by Jack et al. But here I refer to the journal version 2010. This algorithm is a model-based algorithm, and in a couple of minutes I introduce this notion of model-based. So the algorithm is inspired by the UCB algorithm for stochastic multi-arm bandits, but it takes into account that we have state transitions. So it's adaptation of UCB with a careful adaptation of UCB algorithm, which is very famous for multi-arm bandits, to MDPs. So basically, similarly to UCB, you have some unknowns, transition probabilities, and reward functions. You proceed by maintaining some confidence bounds for the unknowns, for the average rewards and transition probabilities. And given these confidence bounds at any time, you choose an optimistic model, which is an optimistic MDP, that leads to the highest gain. More precisely, it does like this. Basically, at each time t, you don't know your MDP, but you can, given your observations so far, and your observations is these empirical things, right? These are your observations. At time t, you know what is this for all SA, and you know what is this for all SA and S prime, right? Given this, you maintain a set of plausible MDPs, or your models, denoted by calligraphic M of t, that are collection of all candidate MDPs and prime, which have the same state space and action space as your true MDP, which you know, and candidate reward functions and candidate transition probabilities that satisfy these. So it says that first you are given a precision, which is your confidence probability. You set it in advance to so 1 minus this is basically your precision. So if you aim for 99%, this would be 0.01, for example. So this is fixed. So for all SA, you look at all distributions mu prime, whose mean mu prime for S state SA is close to your empirical mean in this sense. It should not be deviating from the empirical mean by this amount. And here delta is input, SA you know, T is current time, and this is number of observations so far on this SA. So it means that if you sample SA a lot, this would decrease. And if you sample SA few times, then you have a large parameter. So you have more uncertainty. So this is similarly to what we do in multi-arm bandits. So for reward, average reward is simple. For transition probabilities, recall that we have finite state space and we can just think of probability vectors. So given SA, you have a probability vector empirical 1, and you consider all candidates P prime that are vectors that in the L1 norm sense is close to this empirical 1 by this quantity. And this quantity basically, again, the radius, which is controlled by the square root of this, decreases when you sample SA more often, right? So basically, if you consider all this MDP and prime, you have a continuous set of MDPs, right? We call it MCal of M of T. And we know that these are good models, good MDPs. These are probably those MDPs that may contain my true MDP. And this is the case. It is shown, this is what we refer to as concentration. Basically, it can be shown that with high probability, something close to 1 minus delta, your true MDP falls within this. Then if you optimize over this set of all possible MDPs, over all policies and all possible MDPs, probably you optimize over your true MDP as well, because with high probability it falls in it, right? But of course, if you choose the radius of these two guys carelessly, this is not the case. But these are the rule of these constants and all these complicated things here. So at each time, not only we optimize over all policies, we optimize over all possible MDPs within this model, and we choose an optimistic MDP that has the highest gain among all MDPs and all policies in these MDPs. So having introduced this, we can go towards what is used here. So basically, the algorithm runs in episodes. Maybe episode is not a good term because it may bring a confusion with episodic MDPs. This is, let's call it epochs. So at each episode, let me start from here. You start from epoch number 1, episode number 1, t equal 1, and you are given delta, and you maintain two counters, n, which is number of observation, and v, which is local number of observations. Okay. You observe the initial state and you proceed. You set the initial time of episode tk equal to t, and for the moment, forget about this. You would like to define what policy should be executed during this episode, and you stick to that policy. And when the episode ends, we discuss it later. So basically, this policy P tilde K is the maximum over the gain of all possible policies and all possible MDPs within this model. So basically, we look at the current set of plausible MDPs at this time. We look at all candidate MDPs now, here, and all possible MDPs in M prime. So it's very complicated optimization. But surprisingly, it's done efficiently. It's very surprising, but it is done very efficiently. So the output, find P tilde of K, let's say efficiently, without doing complicated optimizations. So, and to look at this optimization, although it's done efficiently, but look, this is over all possible MDPs, but within these constraints, this L1 constraint and this constraint, right? It's very complicated optimization, but it's there is a magic that this can be done very efficiently. As soon as you find this P tilde of K, your episode starts. You apply this P tilde of K all the time until the number of observation n for some state action pair is doubled. And this doubling is just a trick. You may choose it 3 times, 4 times, it doesn't matter. It's just some stopping time that makes sure that some significant changes in the radius of the confidence bounds has happened. So simply A of t is this function, p tilde of k, because you determine p tilde of k. You apply this, observe next state, observe reward. Go to the next state, go next time, until this thing happens, and then you do this round again. It can be shown that you have like SA log t number of episodes. So this optimization, if it was even complex, would have been done log t number of times after time capital T.
And the SA being the size of the
state action.
Yeah,
space.
exactly.
Yes.
Right.
So let's make sure that I understood it completely. So if you know everything about like the transition kernel and everything, so you can find the optimal policy and then the
Using value iteration.
yeah. So
There's
but-
an algorithm value iteration which is very simple. It's very iterative doing fixed point equation.
But since we don't have that kernel, and since this is unknown, we kind of estimate it first using that empirical distribution, right? Kind of.
It's true, but let's not call it estimated because we estimate the empirical and we consider what would be the set that contains the unknown kernel with high probability.
Exactly.
Yeah, that's what
so you said that I mean by this empirical let's say estimation, by this empirical computation, I can get an MDP which is as surely close to the real MDP, right? So,
by empirical, you mean if I just assume
by
the
this
hat
hat.
and mu hat?
yeah.
Yes.
Right.
Yeah. Well, you can try this, but if you only rely on this, it would be misleading. Yeah. Yes.
So then,
So your question is why not just considering this MDP, p tilde and mu hat, right?
yeah.
Depending on sample pass, it may get a good regret or may get linear regret. And linear regret implies that you are not learning, basically. So basically, I mean, we can discuss it in the context of multi-on bandits. Assume that you don't have any transition probability. If you just rely on mu hat of t to maximize in the multi-on bandit model, depending on the sample pass, the sequence of random things that generated, if you choose your next arm all the time based on empirical things, you may maximize the reward, I mean identify the best arm, or you may just stick to one arm that is suboptimal all the time, or your suboptimal arm may not have the chance to for its estimation to be high enough so that it's selected more often.
But what you can do is that probably you can add something like epsilon greedy to make sure that you do have exploration, but then decay the rate of that exploration.
Yes, that in a multi-bandit you can do. Maybe in the MDP model you can do as well. But the thing is,
here you don't need that randomization anymore because everything comes
yes.
to this empty.
Yeah, well, simple to epsilon greedy you can use here, but empirically this epsilon greedy stuff in practice work very, very badly. And the thing is that usually this epsilon is not any epsilon that you choose. Well, we know that it should decay with 1 over t, for example. But the thing is that it is a more complicated function, even in the multi-on bandit model. It's like minimum of 1 over t and, minimum of d over t for some constant d and 1. And usually this d needs the knowledge of some parameters that are already unknown. So it's truly empirical without any concrete performance guarantee.
Because to me, I mean, this M prime that it is like the sets, the MDP, the model that you get, which satisfies these conditions.
Yes.
This is like the center of all models, and
Yes,
then
yes.
it is that precision, and then so you by this empirical computation you find that center of that of all models, and then you do some like a heuristic search through this circle of models.
We don't do heuristic search. That
M prime is not the center. M prime is the whole set, I guess. Centered over p hat and mu hat, I guess.
it's a bit hard to visualize it. I mean, in the board or something.
Mm.
But let's.
Yeah, you're right. M prime is a set, and then the
set centered over that MDP.
Yeah.
So it's
Right.
just
It's a
that-
collection of all MDPs.
Exactly.
Yeah.
Yes. But
Right.
as an special case, it includes the MDP, you know,
high probability.
that only relies on p hat and mu hat.
Oh.
So if it is optimal, I mean by some chance at time t, it is contained, so it's no risk.
Okay. Yeah.
I guess the good
Right.
thing with this is that you don't have any randomization anymore.
There is no randomization in this. It's
Mhm.
similar to UCB. There is no randomization, and
Right.
yeah, and it's called model-based algorithm because model-based against model-free, right? So there are two big class of algorithms. In this setup or in different contexts, we can have the same classification as well. A model-based algorithm first maintains some models, candidate models, and choose, the one that is optimistic in the sense that that leads to the highest maximal objective function that within the problem that you're looking at. Within the models, within the candidate models. So basically, it says that you don't have mu and p, so I consider all the models with confidence bounds created around mu prime and p prime, and I optimize within these candidate models. So this is that's called model-based. We can have model-free, and these are, for example, algorithms like Q-learning. In Q-learning, although in a different context, you don't know p and mu. You know what is your discount, status space, action space, right? That's it. But instead of creating confidence bounds or considering candidate models for M prime as this, you just maintain Q function and you just act based on your empirical Q function, right? So an algorithm like Q-learning, in that sense, is model-free. It does not maintain any model because it says my goal is not estimate to model. My goal is to maximize the reward, and I can maximize the reward without creating the models.
Right. Yeah.
So it's a different approach, but although so semantically maybe model free is better because you are estimating the model and maximizing over the set of models, and you identify what is more or less close to the best model, and you proceed. But you do not need. Maybe it's better just to go for relevant quantities such as Q function, for example, because we can define Q functions in this case as well. It's very similar to Q-learning. But what we have seen so far is that the most successful algorithms, if you exclude deep learning and stuff, most of successful stories happen when you, with performance guarantees, when you go for model-based. So these are both theoretically and empirically more successful, this model-based. But I would say any of these methodologies have their own friends or supporters. But just keep in mind this is model-based.
Have you also seen some relative results from sequential model, the sequential estimation, and because this is also like in a sort of
too much thing you can do about this center here. This is the solution to maximum likelihood estimate. So this is the best. I mean, this is the only. So this p hat and mu hat, we cannot go for better thing. But for this radius and for this L1 norm, yes. I mean, this L1 norm, we can argue that this is. I mean, it simplifies optimization, but it's ridiculous because it models the uncertainty by polyton. Whereas optimally, we know through lower bounds that we do not have time today to discuss, but maybe later on, it should be modeled by more complicated things such as KL divergence. And it's not because of the fact that KL divergence is fancy, it's because there is a lower bound that signals us, that it should be KL, not L1 or something. So it's interesting that this.
If everything is, let's see, if if the alphabet is discrete, then they have Pinsker inequalities.
So
they
Pinsker and
wouldn't be-
KL are, friends.
Yeah, I know. So they wouldn't be fundamental different because this L1 norm is total variation, and total variation and KL they're related, so not fundamentally
Yes.
different.
So
That's a special
basically,
case.
basically, when you talk about bandits, it's a matter of like matching constants for the lower bound, right? And maybe by Pinsker you may lose a little bit, but it's simpler because it's like what you do in UCB, right? But if you do KL, you have better constants, but empirically better performance. But when you come to complexity of learning in a bandit model, it's just number of arms appear, and then it's Pinsker there looks very very good. But here we discuss a bit later that when you look at the regret bounds, basically you have states, actions, number of states, number of actions in the regret bound, and also another notion that is because you have MDP, you have to traverse from this to this. Basically, imagine this: if you know what is the optimal algorithm at this state, you may go there. Under a suboptimal algorithm, you are learning, right? You have to try suboptimal actions. You may go here, and because of the fact that the optimal algorithm is gone up, maybe in the future it comes, state transition brings the optimal algorithm here, an agent under an oracle agent basically, who knows what is the optimal algorithm. But under suboptimal algorithm, you may come here, but you may realize, okay, now I have learned the optimal policy, but you are here and he's there. And to catch this, you lose some reward, and to account for this, you have another thing beyond what we have in bandit. Less surprisingly, this is captured by diameter. Yeah, well, it could be controlled by diameter because it's a thing that you travel. But more recently, we have shown that it can be captured by more refined things than diameter, because diameter could be very very large, basically. And there are strong arguments that it should not be diameter. You pay less penalty, basically.
You mean diameter is probably too conservative?
Too conservative, yes, because it just captures what is the span of bias function, and this bias function, the span is the range. Sometimes you pay less penalty depending on the shape of bias function or value function. So if you change these candidate MDPs, you may get another algorithm. We have a couple of other algorithms with different performance guarantees, but let's just to conclude maybe today's session. What is
another thing?
Yeah.
So in the end, this result gives you something with high probability, and then
we would like to minimize regret. So up to now, I have not shown any result. So basically, what
results here in this slide.
Yeah.
That was okay.
No,
go on then.
it's
Yeah.
both. Yes.
Yeah.
But so I interrupted because to emphasize that not only I would like to identify the optimal policy, not only I would like to do that, but also I would like to minimize my regret, because in the end, if you say after 10,000 or I don't know 1 million time slots, I found the optimal policy, somebody would say, okay, I do not care. But if you say I minimized the regret, or I bounded the regret by this amount, it says, okay, if I knew what is the optimal policy, if I was an oracle, then I would gain this much, which is sublinear, for example, in the time horizon, with this constant. So this is the performance guarantee of UCRL2. The first one is a high community regret bound. It says that the regret is bounded by 34 times diameter times number of states, the square root of AT log of T over delta, with probability at least 1 minus delta. So the better delta you choose, the smaller delta you choose, you increase this confidence. Still, you just harm a little bit, you just harm your regret bound a little bit because it's just log of t over delta. Right? For example, if delta is 1 over t, it would be log of t squared 2 log t. If delta is 1 over t squared, which is much better confidence, it would be square root of 3 log t, right? But diameter is here and number of states is here. Well, a little bit later we discuss if this is good or if we can improve this or not, because this is the important thing, right? And we can judge it through the lens of lower bounds. Right? We have this upper bound on the expected regret, basically up to some additive constants, which is not a function of t, but a function of parameters determined by your MDP at hand. These include mixing times and stuff, but these are finite anyway. The regret is upper bounded by d squared s squared a divided by delta log t. And here there is a missing constant, I forgot, but this is 34 to the power of 2. So it's big constant, but this is not a square root of t. This is log t. This is log t, but you know you have bigger constant and you have delta here. So it's problem dependent bound, as we have in bandits. In bandits we had log t bounds, like number of arms divided by the gap here, delta times log t, plus some constant. And we had also a square root of k number of arms times t, log t.
Right.
So this delta is something that makes these things big comparable to the square root of t. So it's so what I'm saying is not very precise, but this delta could be very small. So just keep in mind. But if it's very, very small, then you may get this square root of t stuff, because if it's smaller by 1 over square root of t, then you can bound. So it's a bit different story. I may not go deeper here, but just let me describe things here. So there is a big missing constant missing here. This delta is the gain, the difference between what you would achieve under G star minus what you would achieve under the second best policy. So if you sort all the policies depending on their according to their gain, there is the optimal policy G star, and then a second best policy, which is not optimal, so it would be G star minus, and this delta is that difference, the gap from G star minus to G star. But this is a bit conservative, and this bound can be improved, both because of delta here, and because of this d squared, and because of s squared. Why? Actually both of bounds. Because of this, to see whether this upper bound is good, we reviewed the lower bound, minimax lower bound by Jack et al. In the same paper 2010. So it's a minimax lower bound, and this type of minimax lower bound, they come up with a problem with a very, very hard to learn MDP, for which they try to bound the expected regret from the lower. So basically the result is this: for any time t, there is an MDP with S states and A actions such that any learning algorithm, it's not for UCL, for any learning algorithm, cannot have regret better than this, square root of t SAT. So in that sense, it says that to this expected regret, so just look at this, not this, because we may come back to this later. We only, so up to constants, we only can improve these results by a square root of ds, probably, because we don't know if the lower bound is tight, right? the lower bound says square root of a is there, square root of t is there. Log t is, you can ignore it because, it's logarithmic compared to a square root of t. But lower bound has a square root of t, a square root of s, a square root of a, a square root of e. But here we have ds outside of square root. So in the best case, if the lower bound is tight and if the upper bound is bad, in the best case, the square root of ds can be shaved off. But we don't know, maybe lower bound is tight, this is bad, or maybe this is tight and lower bound is bad. We don't know yet. And the gap is not closed. Actually, the gap in the literature is closed. Because this S, not for this algorithm, but for a wiser algorithm, it is improved to a square root of S. So we know that the lower bound up to this SAT is tight.
This notation,
This is gamma, omega.
so it means that, is it the t is finite, right? So it would be any value, or is it t?
The t is parametric, but this t is any value, but non-asymptotic.
Okay. So then
But
that
this is just
notation-
Heinz constants.
So but that constant comparing to the DSAT, so
These constants are independent of DSAT. These omega Heinz constants that are independent of DSAT. So these are, I could remove it and I could put actual constants, and the constants are like 0.01 or something.
okay, yeah.
A small constants, which is bad because it's lower bound. We would like to have high constant, and to remove that gap is very, it requires a lot of effort. But the thing is that we would like to see what is the complexity of learning, what is the hardness of learning, and for multi-arm bandit, we know that this is for multi-arm bandit, diameter is meaningless, S is meaningless. We have AT, right, and we have a square root of AT. But this result says when you consider an MDP, it is as if you have SA arms, and you have also diameter as well, because you are brought to somewhere else, and you should come back to that, and you should pay for it. And with this minimax model, it says that what you would pay is a square root of D, but it's one possibility. Since it is not the gap is not closed, maybe it should be something else. It should not be a square root of D. But it is at least a square root of t, because we have one problem in sense, where non-asymptotically, after these finite time steps, t is not necessarily infinite. For any t greater than this, you incur this regret in expectation. But it's good if I bring. Okay, let me say how the proof proceeds. So the proof basically relies on the techniques that for a similar result for multi-arm bandits. The minimax lower bound for multi-arm bandits, which is done in 2002, right? Which is both for adversarial and stochastic. So, but to consider the case of Markov decision process, it will requires a lot of effort, but mostly tricks and computation. But,
So, can you go to the previous slide?
yeah, but before that, let me finish up with this about proof. So basically, for this proof, they look at the simplest possible MDP, so that you make it very hard for the learner to distinguish between two actions. One is good, and one is something close to good. And in the case of multi-arm bandit, you have just reward distribution. In the case of MDP, to simplify the life, you fix the reward distribution. You let the learner know what is the reward distribution. You give it to him. But you don't give to him, to her, the transition probabilities. And you just let the optimal action, under optimal action, you go to like the heaven state, the state that gives you a lot of reward from the bad state, under a slightly different transition probability. So under suboptimal action, so it's like this. So you have a bad action, you have a good action. You are brought here, So as soon as you are in the bad action, you would like to go to good action. Under some optimal action, you go under suboptimal action, you go with probability delta to good action, and you stay with 1 minus delta in the bad action. Whereas, so there are a few suboptimal actions. Under all of them, you have the same transition, and you do the same here. You stay with probability 1 minus delta here, and come back to this bad action with probability delta. But there is an optimal algorithm that goes from bad to good action under a slightly different transition probability, which is delta plus epsilon, and stays in the bad action with 1 minus delta minus epsilon. So basically, if you receive the reward deterministically 0 here and 1 here, it is apparently optimal to choose when you hear the green one, right? Right? Because, you know, it gives, it's optimal, right? But the thing is that if you choose this epsilon, this delta is fixed. Delta is not that delta, it's let's call it, yeah, it's input, it's fixed. I mean, you choose something like, for example, 1/3, one half. But this epsilon is chosen to be, I think, something like proportional to, at least, A over ET as a function of t. That's why t is fixed at the beginning of the problem, because it holds for any t. It's non-asymptotic, but it's t in the sense that your MDP is as a function, it's formulated as a function of t. And because of this form, well, you should go through the analysis to see why we select this thing for epsilon. And if you choose this, it is very hard for the learner to distinguish between these two, because delta and delta plus epsilon are very close, and you have to try a lot of time. Of course, after some time, the learner gets to know which is the best. But the thing is that after trying this, because of this specific epsilon, the regret is penalized by this difference, the difference of the reward that in expectation would be attained under this or under this. And because of this, you get this square root of DSAT. But after like 2-3 pages of crazy computations. It's not very, but it's just very sketch. And the MDP constituent is not as simple as this. It's very, you know, compact representation. It's like tree-like MDP. But in every leaf, so to say, you have this type of two-state MDPs. But it's based on this methodology of considering hard-to-learn MDPs. So these are like very worst-case minimax bound. So it's good because, you know, it gives some lower bound, and without this lower bound, we don't know if this square root of t is bad or square root of s is bad, or what is good or what is bad. We know square root of t is not bad because, you know, in the worst case you pay this. But this type of regret is restricting in a sense that, you know, it is derived for a minimax problem. It's derived for a very hard problem instance, maybe the hardest possible. Or maybe something that the hardest possible is a bit harder than this. But in most states are simpler than this. So we look for lower bounds that are that are a function of your problem, not my specific very pathological problem. These are just to, you know, derived by computer scientists to see, yeah, well, to anchor this result. They provide information, but, you know, in a limited sense. But next time we go for problem-dependent bounds that gives what is the lower bound of your MDP, not my very magical pathological MDP.
So one question, can you go now back to the previous slide? Let me take t equal 1 for instance.
So you, yeah, well, we cannot because here.
No. Go forward. Yeah. Back. The previous one.
Because it says after t.
No, here.
Okay.
in this one, the first, the regret is lower.
It's not full statement of the theorem.
Yeah,
It's
there's usually
t
like some
equal
sort of
greater
minimum.
than it's t greater than 2 actually.
Okay, let's
Because
so
of-
t is 2.
Yeah.
I want to see the order. So let's say
Yeah.
let's say that the S is also binary. You have 2 states, and then the alphabet is also 2. So then in the end, that regret, what is the, so it is the sum of the R parameters, right?
One thing you consider 2 states. Okay, before that, because we should look at diameter anyways, right? What is the diameter of this MPP?
That's the thing. So I want to one. It depends
No,
on the.
it's 1 over delta. It's the number of time steps in expectation. You know, if I start from this is a geometric series, right? What with probability delta, from this state to this state, right? I come with probability delta plus delta 2, delta 3. If you sum it over, all possible events, the diameter of this will be 1 over delta. So this diameter could be as bad as S, but also, as bad as these probabilities. So if you consider these 2 state MPPs, S is 2, A is, let's say we have 2 actions. Actually, imagine, 2, 2, and this D is 1 over delta. And this delta, depending on delta, your learning could be, well, the best case, delta is 0.5.
But
Sorry.
That delta is the same as that delta.
No, it's not that delta.
Okay,
it's
so,
not. It's let's call this
One.
C.
Yeah. Okay.
Yes. Sorry, it was.
Yeah.
And the diameter is this. If you do not like this delta, you can choose it 1 over capital T.
So then, how would you choose that C?
Okay, let me do it like this. Maybe it's better. If delta is fixed, it's good because as a decision maker, you have an algorithm whose input is not as a function of t, because we would like t to be not fixed, right? If an algorithm takes t as an input, is not very good. Because it's very restricting, because maybe something is in the analysis or design of the algorithm that requires this. But if the algorithm does not require t as an input, capital T, it's called anytime algorithm. So it's the other case is called the algorithm that requires the knowledge of time horizon. But for the moment, for comparison, or just to a better thing. Let me fix delta to be 1 over t, right? Then, with probability 1 minus 1t, I incur this regret, okay? Of course, upper bounded by this. Square root of 2, okay? And with probability 1 over t, I incur what? I incur the maximum regret, which is 1. In each state times t. Right? Because there are t steps, and of course it depends on the range of reward function, the range of support of transition probability, but assume that it has bounded support. So I am saying that expected regret of UCRM2 yes, is less than this. Well, I can forget about this because this is bounded by 1 anyway. It's 40 ds of AT log t plus some constant. That is depending on your transition probabilities. But here is 1, I mean, for the case of Burnetas.
So you assume that the R function or the R values are like limited to some.
Yeah, bounded support. if it's not with bounded support, we can, because what we need is to look at the expected value of the reward between the optimal and suboptimal, and in expectation, if it's not heavy tailed, of course, it decays. But for simplicity, if it's of bounded support, it's this high probability thing is not limiting, because if you like, you can.
And then you can always fix your precision and then run the algorithm.
Yeah, it's like this all the time, but just to look at the expected regret is just to choose this delta as a function of, for example, t, for example, 1 over t or 1 over t squared, because after all, your regret per step is bounded, and then the probability that you go for the worst case bound is like 1 over t or 1 over, something limiting. And here, this is less than 1. Right? Yeah, well, what I'm saying is that as long as this this precision parameter delta is in the log, it's safe, for sure. What I'm saying is mostly this. Okay, next time we continue with this.
One thing that
for
in here, it says that after t greater than dsa step.
yes.
I can imagine what's the meaning of SA, simply because you need to have an estimation of mu and nu for all S and A, well, estimation of P and mu for all SA, so you need at least SA steps to be able to compute that. Does make sense, but what?
Basically, from
D
this
here?
minimax lower bound, you should not. You should get some insight, but not too much.
No, it's not about insight,
Yeah,
it's just about how they start
It's
the
art.
proof.
I would say this in the first sight, it's artifact of the proof, but maybe you cannot do better than this.
Mm-hmm.
So it happens algebraically, actually, in the process of the proof, that you would like to. Well, there are some terms you would like to bound anyways, and to do that, one possibility is to consider that your t is still finite, but is above something that makes your life a bit easier. And as soon as you choose this, which is not very bad, by the way, because it's finite, right? And it's also, it has an intuition, because it says, we come back to this, but this can be improved for sure, not for SA but for this D. But this is chosen because of what appears in the proof.
Okay.
Right.
So, for example, if you choose 10 times this, you get better constant in the proof, actually. But I think a good question. This SA probably is there. You cannot avoid it. But from this D to something else, for example, some other thing, at least for this specific problem instance, you cannot avoid it probably. But this is just one instance. Maybe there are better instances.
Right.
Okay, so no actual insight, just a trick to.
It's
have some
that's way.
inequality.
So if you look at what we do next time, which is the Burnetas and Katehakis algorithm, lower bounds and algorithm. So for Burnetas and Katehakis, the regular lower bound that we present is problem dependent. So it is actually a real lower bound in a sense that there is an algorithm that achieves that lower bound, and that lower bound is gives the key for geometry of your problem, which is good. But here, things that are derived constant, you should not scrutinize too much, because it's based on pathological instances that are useful in a sense that they provide good lower bounds, big lower bounds that we want. But maybe there are better, and the research for that is ongoing. I mean, there are people who would like to, not too many, but who would like to improve the constant, even for simpler problems, so that they may match the numerical constants here to what is achievable under algorithms.
Right. Yeah.
But don't spend much time on this, because these are based on just very minimax favoring pathological problems.
Okay, great. I guess that we have to close this station.
Okay, we stop here and then
Continue next session.
there are like 10 slides left, but these 10 slides will complement this in the sense that we go for better lower bounds that given this knowledge will bring you know, will complete whatever picture you have right now.
Exactly. Okay.
Okay, thank you.
Good. Thank you.
Thank you.